At this juncture, we are going to look at how to draw a PERT network, project evaluation and review technique network. You'll find that there's substantial difference between critical path method network and PERT network. One thing that will stand out a lot is that PERT network is probabilistic. Now, for us to come up with a PERT network, there are a number of steps that we must follow. The steps are, first of all, we should prepare a table showing the estimate time for each activity. Now, the estimate time will be the time that we'll obtain from optimistic time, most likely time, and pessimistic time. There is a formula that has been given in the previous part of this lesson, how to calculate that. In some cases, you may find that some of these times are missing, but you'll be given others. For instance, you may be given an estimate time, but you're missing most likely time. In that case, you have to restructure the equation so that you are able to get that. This kind of problem is, props up, especially when you are given a table to fill, where you are given some times and you are missing others. So in that case, you have to evaluate these times. Alternatively, you may also find a case where you're being asked to get the standard deviation and variance of the estimate time for each particular activity. In that case, you'll also use the formula that has been given earlier in the lesson to do that. So once you have the estimate time, you draw the project network of activities based on the estimate time of those activities. Now, after that, you can find out what you want. For instance, you can find out the part that is that will most likely take the longest. Sorry. You may also find out the activities which are crucial, or the ones which may be parallel, and so on and so forth. Remember that in this kind of network, we don't have what you call a critical path. We don't follow a critical path because the network is probabilistic, meaning that whatever path that you get taking the longest will be probabilistic in nature. It does not mean that it will always hold. Sometimes it may hold, sometimes it may not. So that's that. But that particular path will be the one that has the highest possible possibility of becoming the time to be taken. Just to remind you, there are two types of symbols that we use in a network. We have what we call an event. An event will have an event number, the earliest start time or the earliest finish time on the top right quadrant, and the latest start time or the latest finish time in the bottom right quadrant. So on the other side, we have an activity. An activity is always an arrow. It can be either dashed or a solid arrow. Activities always point toward the right because that is the flow of time. Time flows from towards the future. So okay, now we've been given this PERT problem. We've identified separate activities which are associated together, and we have been told to draw a PERT network for the project. Now you'll discover that you're given three types of times. We have what you call an optimistic time, we have a pessimistic time, and the most likely time. We assume that actually it's not assumed. We've been told that these times are in form of days, as shown. So in this case, what you're going to do is we'll have to calculate the estimate time based on these times that we've been given. So for the first activity, we'll have 7 plus 9 plus 4 times 7, and that will give us 28 plus 9, which is going to give us 28 plus 9 is going to give us 37 plus 7. It's going to give us 44 divided by 6, and we'll get that to be 7.3. And it's a recurring figure, so what we'll do, we'll round off to the one decimal place, and we'll get 7.3. It's going to be 7.333, and we'll round off up to the nearest one decimal. So having gotten that, we'll evaluate times for the others. There'll be for the case of 7, you'll discover that the value will remain as 7, because 28 plus 14 will give you 42. 42 divided by 6 is going to be 7. So that will arrive at that. So it means that the estimate, if all the times are equal, the estimate also will be equal to the other times. And I think that is something that had been talked about in the previous session. Another thing that you'll observe is that maybe when you are working out the table, is that you'll find that the time that you get, the estimate time, tends to hang around the most likely time. The case of B, we have the optimistic being 2, pessimistic being 11, but the most likely time being 6, and the estimate is 6.2. Another case on point is C, where we have the optimistic being 11, pessimistic being 22, most likely being 16, and then we have the estimate being 16.2. So you'll find that the figure that the figure that the estimate always lies around is the one around most likely time, and that can give you an idea whether you are having your figures computed correctly or not. Having gotten the estimate figures for all, we'll use those times to draw a network. Remember that we had the initial event starting at 0, and the activity takes 7.3 days. So we'll have the end event for that particular activity being 1, and it will be reached after 7.3 days. We'll have another activity B starting from the initial event 0, and this particular activity will take 6.2 days. Therefore, the head event of that particular activity will be 6.2. Now we have, and C is a combination of A and B. That means that for C to start, A and B should stop. So if you look at the two together, A takes 7.3, B takes 6.2. So it will mean that for both A and B to give us C, we'll have to wait for A, because A takes a bit longer time. That means the time that C is going to start is at the earliest 7.3. So 7.3 plus the duration, the estimate duration of C, which is 16.2, will give us 23.5. Moving on, we'll have the next activity, which is D. D takes 11.2. Now, since they are converging at that event number 3, and remember that you are working on the earlier start time, and in this case, if you may remember, when we were working on CPM, we said that whenever you're evaluating earliest start time or earliest finish time, we always take the larger value. So in this case, we'll have 23.5 versus 11.2. You'll find that 23.5 is the larger value, meaning that activity C will take longer to complete than activity D, meaning that also D has some float. So we'll have it as that. So the end event for D will be 23.5. We'll have another activity, which is E, and E comes after C and D. And remember that yesterday, when you're talking about the CPM, I say that you have to see, you have to evaluate your table, so that you can know the kind of organization that you can have for your network. Like in this case, I was able to see that E will be combined. It will have a combination of both C and D, and I have arranged them in order. So in this case, we have E taking 16.7. So we'll add that on top of the time that we have in that event number 3, and we'll arrive at the end event of E having, or E stopping at 40.2. F. Now F will bring some some new adjustment into the network. Initially, we add C connecting directly from event number 2 to event number 3, but now we have we have been forced to introduce another event here. Now, if you look at F is only dependent on C, meaning that it does not depend on D. Now, the reason why we have to separate it is that sometimes, and this is not in most cases, sometimes you may find that event number D may end up taking longer than event number C. And if you had drawn your network such that F comes from E, you'll have two problems. First of all, you will encounter two activities, that is F and E, starting from event number 3 to number 5. Secondly, you'll have forced event number F or activity number F to start after D has stopped, yet it's not independent. So to resolve this kind of problem, we have C terminating in its own head event, which is numbered now 4. We'll restructure the numbering. Then using a dummy, we'll bring C and combine it with D to get activity E. And from that, we'll also have C generate F on its own, so as shown. So if you can look at F is only dependent on C, but E is dependent on D and C through this particular dummy. And just as a reminder, you'll see that the dummy is drawn in such a way that it tends to flow towards the right hand side of the diagram. I remember that yesterday I stated that whenever you're drawing an activity in a network, you make sure that it's either pointing towards the right hand side or at the very most vertical, that is either moving up or down, but it should not move towards the back, that is towards the left hand side. So with that restructured, we'll find that activity F takes 7.0 days to complete. So when we add that 7.0 on 23, we'll get 30, and 30 is less than 40. Therefore, it means that the value that we had initially will hold. Then we'll get the next activity, which is G, coming after combination of both E and F, and this will take 4.5 days. So starting at 40.2, we'll add that 4.5, we end up with 44.7, and that will have, with that we'll have finished what we call our forward pass. So next session is what we call the back pass, and remember that in the last event, the earliest start time and the latest start time, or the earliest finish time and the latest finish time are equal. So we'll make the two equal, that is 44.7 on top and bottom, and as we walk back, we'll have 44.7 minus 4.5 for the duration for activity G, and we'll get 40.2. Walking back, we'll have 23.5, have 27.3. Also through a dummy, we'll have 7.3. 0. So having drawn the network, what is the next thing that we'll do? Using that particular network, you can identify the crucial activities that are there, the activities which require resources allocated in time and in an orderly manner. We'll also have identified the activities which are the order of activities that we have in a network, and the ones which can be allocated certain resources at a particular time. Using also this particular type of diagram, we'll be able to estimate the project completion date. And remember that this is going to be an estimate because PERT is a probabilistic diagram.